Welcome to Lecture 10.1, Optimization by Parametric Sweep for Introduction to Programming in Mechanical Engineering. By the end of this lecture video, you'll have an understanding of what optimization means in engineering, what it means to optimize by parametric sweep, and how to apply that to bridge design. This slide, the table of contents, contains hyperlinks to each of the sections to make the downloaded PDF easy to navigate. Now, the word optimization is used all the time in engineering. These problems can be very simple, or they can be extremely complex. In general, to optimize means to maximize or minimize one or more performance metric of a system. For example, a part's weight. There's usually at least one constraint on this. In engineering, we consider things like safety or the cost or the material usage, many other things. This lecture is intended as an introduction to the concept. Here are just a few of the mechanical engineering courses that will incorporate optimization in some way. First, we have Introduction to Thermodynamics. We have Statics 2. We have Data Science for Engineers, which is the second and the third courses in this particular sequence. We have Dynamic Systems, and then Thermal Systems Design, and many more. There are many different kinds of optimization. Some of the methods are designed for very specific cases, and they will have both pros and cons. This lecture and the next will only cover two methods. We have parametric sweep, which is robust in that it accurately returns the global extremum within the domain, but it can be very slow. And we have gradient descent, which is faster, but it's only guaranteed to return the global extremum if the function is known to be unimodal. That is something that we'll talk about more in the next lecture. Now, all problems have at least one variable that you can adjust as the designer to vary the solution performance. This is a parameter. For example, you could laser cut from either cardboard or wood or acrylic or even 3D print parts for your MEMS24 rovers. A parametric sweep means to test a domain of values for each parameter and evaluate the solution performance. In this example, that would be the material that you choose. You would test each of them on your rover. The optimized combination of parameters performs the best according to your solution performance metric. Now, there are very few engineering problems that are simple enough to reasonably do a manual parametric sweep like that. Even with that rover, you might not have time to test each material given that there are 40 other groups also trying to make their parts. That's before you even consider all the architects and the bioengineers. Computation empowers you to run thousands of tests before you ever approach the machines in our makerspace. To illustrate this particular method, we'll consider the simple Warren truss given here. It's pinned at one side and it has a roller at the other, and we're just going to consider a singular nodal force at the center there. Now, this truss has two parameters, technically, the angle theta, which is called out, and the length L between the two supports. In the Statics 1 project, that length is fixed, so we won't consider that as a parameter. Our optimization metric is called the performance index, or the PI. Its formula is given at the bottom, where its weight held is divided by the weight of the truss itself and the cost of the truss. To perform this analysis, we'll vary theta and then evaluate the bridge's performance for each iteration. Before we get into that, I just want to give a couple of caveats. First of all, I make several simplifications here from the Statics 1 project itself. For example, I don't consider that the main beam is actually bigger than the rest of the truss. And this analysis from Statics 1 also completely neglects complexities like bending and distributed loading. So we should expect our actual bridge in real life to differ from the predictions made by this code. Lastly, I'm not going to cover any of that statics analysis with the system of equations. That is for a different class. Now, because this lecture focuses on just the implementation of optimization and not statics, the next few slides will omit a lot of detail. The codes for evaluating the bridge's performance will be included, but only in the appendix. We'll leave that as a black box magic function until that point, and you can read through that if you're interested. Now, just to show you where we're going, here is the entire code. We're going to break that down now, starting with defining each of the symbolic variables. We have the 3 reactionary forces from the 2 supports, as well as the internal reactionary forces in each of the members, A through E, and the applied load as well. Then we define an anonymous function for the right-hand side vector of the system of equations. In this case, the load is only applied to that singular node from before, so we only show up in that one location in the vector. Then we can define our array to test different values of theta. We'll call that theta values, and it'll go from 1 to 89 because 0 and 90 are not valid degree values for the bridge's characteristics. Then we can just initialize a couple of arrays and that variable to store our results. Previous load will get updated with each iteration, and then we can define our loop itself. Our looping variable is theta. That will vary according to the array theta values. It'll take on a new one of those values with each iteration. The first thing in that loop is to define the symbolic equations. I'm omitting those because they take up a lot of space, and that's not the point of this lecture. But we can package all of those equations up into a vector called equations, and then use the function equations2matrix to turn that into a coefficient matrix, which we store in coefs here. Then we can use that black box magic function evaluate bridge, using a load, a value for that angle, as well as the material constraints on the strength properties and the coefficient matrix and that right-hand side vector. Then we can store the results from that, the load capacity and the performance, in their respective variable locations. Here's some plotting just to wrap all that up, and that provides us with the following figure here. We can see that there is a very clear maximum in the performance index right at the angle equals 60 degrees. That right there is the optimal value of theta for the Warren truss. Note that the load does not start to decrease after 60 degrees. It does continue to hold more weight the taller that you make the bridge. But we have to consider, first of all, is it reasonable to make a bridge that tall? But more importantly, the bridge is performing less efficiently after 60 degrees, and that it's not holding more weight per material that you're putting on there. So our performance index is our guiding metric. Now, in summary, optimization in engineering means to maximize or to minimize a performance metric for a system, especially under some constraint. To optimize by parametric sweep is to evaluate that system for many values of one or more parameters. The best configuration is the optimized design based on that. In the context of the Statics 1 bridge project, the variable theta is the only parameter for our particular truss, so optimization consists of varying that angle over the possible domain. The project defines a performance metric for us, which is the performance index, and that's what we want to maximize. The sweep gives us a picture of the whole domain's performance, and we can use that to pick the best design. Now, the appendix will have several slides to provide all of the code that is used in this analysis, except for that system of equations. Each slide will show a body of code, which is then followed with some slides that call out any of the functions that are called within that body of code. And then those functions are defined in the following slides all the way up until the end. Here we just have the main code again. We're calling out the evaluate bridge function, which gets called. That gets defined here. There's a whole bunch of stuff, and that calls the evaluate stresses and evaluate performance functions. So we'll define those. We have evaluate stresses. This calls evaluate areas, so we'll define that. And then we can evaluate performance. This calls evaluate cost and evaluate weight. So we'll define those here. We have evaluate cost and evaluate weight, both of which call this evaluate length function, and so we'll define that finally.